Okay, so hi, I'm Josh. This is joint work with Virginia. And yeah, so I'm going to tell you about further limitations for the known approaches for matrix multiplication. And I guess in order to do that, I first have to tell you about what the known approaches for matrix multiplication are. And that'll probably take up a lot of the talk. So let's get started. So matrix multiplication, the problem we're dealing with is we're given two n by n matrices x and y, and our goal is to compute their product z. You can think of these are matrices over any ring you want, and we're working over a computation model where like arithmetic operations like addition and multiplication take constant time. So of course the naive algorithm for this takes n cubed time, and I'm sure a lot of you have seen Strawson's algorithm from 1969 for improving on this, but let me just remind you how it works. So the idea is you take your matrices x and y, and you divide them into these 2 by 2 block matrices like this. And then Strawson comes up with this really crazy identities. So he computes these 7 products of a sum of x variables times a sum of x blocks times a sum of y blocks. And he notices that the 4 blocks of z can all be written as linear combinations of these 7 products. So normally it would take 8 multiplications to do 2 by 2 matrix multiplication, but here he does it with only 7. And then this leads to a really nice recursive algorithm where the idea is to do n by n multiplication, you do these 7 n over 2 by n over 2 multiplications, and then plus just order n squared time to do all the additions and subtractions and stuff. And this gives a runtime at the end of n to the 2.81 about. So in order to generalize this to the more recent matrix multi algorithms, I'm going to rewrite it in a different way that has to do with a tensor rank bound. So I think probably a lot of you know what that means, but let me say it anyway. So for this talk, x, y, and z are going to be sets of formal variables. You can think of these as the blocks of the x, y, and z matrices. And then for our purposes, a tensor is going to be a trilinear form that looks like this, where basically for each triple of an x variable, y variable, and z variable, we have a coefficient that's, well, it can come from any field. Let's just think of it as a complex number. So for every triple of an x variable, y variable, and z variable, you have some complex number in front of it. So what's the rank of one of these tensors? Well, we say it has rank 1 if it can be written in this form, if it's a product of a linear combination of x variables times a linear combination of y variables times a linear combination of z variables. And then more generally, the rank of the tensor is the minimum number of these rank 1 tensors whose sum gives the tensor T. So if you this definition is really similar to rank of matrices that you probably may be more familiar with. So how do I rewrite Strawson's algorithm as a tensor rank bound? Well, here's Strawson's algorithm again. And well, I have these nice bilinear forms on the left, and I want to turn them into trilinear forms. So let me show you what I'm going to do by example. So starting with M1, I'm going to find all the places on the right where M1 appears, and I'm just going to multiply M1 by those z variables. And then similarly, for M2, I'm going to find all the places where M2 appears, and I'm going to multiply M2 by those z variables. And notice we had minus M2 for Z22, so I multiplied by minus Z22. And similarly, we'll do this for all 7 of them. So now on the left, we have 7 nice rank 1 tensors. And what happens when we add them all together? Well, to start, what's the coefficient of Z11 going to be when we add them all together? Well, notice Z11 appears in exactly these same places as we set it up, as Strawson's identity shows it's supposed to be equal to the function of x and y that Z11 should be equal to, right? So the coefficient of Z11 is going to be that same thing, x11, y11 plus x12, y21. And similarly, the coefficient of each z variable will be what it's supposed to be in terms of the x and y variables. And you can rewrite this in terms of this really nice symmetric looking tensor here, the sum of xij, yjk, zik for ij and k from 1 to 2. So what we showed is that this tensor, which is called the 2 by 2 by 2 matrix multiplication tensor, has rank at most 7 because we wrote it as the sum of 7 rank 1 tensors, even though it has 8 terms, and a priori you might think it has rank 8. So more generally, a matrix multiplication tensor is defined like this, which is exactly the same as the tensor we were talking about before, but instead of 2, we can replace it with any integer m, and it's denoted by this m comma m comma m thing. And you can see by the same kind of recursive algorithm idea that if you can show that the m by m by m matrix mult tensor has rank at most k, then that means matrix multiplication, the algorithmic problem, can be done in time n to the power of log base m of k. So like before with Strawson's algorithm, m was 2 and k was 7. So in fact, omega, like the exponent of matrix multiplication, is often actually defined as the minimum or the lim inf over all m of the log base m of the rank of this m by m by m tensor. So matrix multiplication can be done in n to the omega time, and in lots of models of computation, like the arithmetic circuit model, you can actually show that algorithms kind of have to be of this form, and this actually is the amount of time that matrix multiplication has to take. So the goal in designing these algorithms is to give rank upper bounds for matrix mult tensors. And so for instance, Strawson gave a rank upper bound for the 2 by 2 by 2 tensor, and about 10 years later, Pon gave an upper bound for the 70 by 70 by 70 tensor, which you can use to improve the bound on omega a little bit. But looking at these cases like this quickly becomes really unwieldy, I think at least. So more modern algorithms use different approaches based on what's called border rank. So the border rank of the tensor is defined like this. So the border rank of a tensor T is the smallest number R such that there's a sequence of tensors, T1, T2, T3, such that each of those tensors has rank at most R, and such that the limit of that sequence of tensors is our tensor T. So T has border rank R if there's a sequence of rank R tensors that converge to T. And what's nice about this is that Bini showed in 79 that instead of looking at the rank of these matrix mult tensors, we can replace it by the border rank in this expression and still get the exact same kind of bound on omega. And it's not hard to see, the border rank can often be smaller than the rank. So this is seemingly an easier way to go about proving these bounds on omega. So our updated goal now is to give bounds on the border rank of matrix mult tensors. So I think this is kind of a complicated notion, so let me give you an example. So let's look at this tensor A here. It's like the 3 terms that have 2 subscripts 1 and 1 subscript 2. And this tensor A has rank 3, but I'm going to show you quickly that it actually has border rank 2. So how do we do this? Well, we're going to use this other tensor B, which actually does have rank 2. Here's a nice rank 2 expression for it. And when you expand it out, it's like all the terms that have at least one of their subscripts is a 2. And this rank has rank 2. So now we're going to transform B in a particular way. What we're going to do is we're going to pick a really small positive number epsilon, and then in both the expressions for B, whenever x2, y2, or z2 appears, we're going to multiply it by epsilon squared, and whenever x1, y1, or z1 appears, we're going to divide it by epsilon. So what do we get? Well, here are the 2 expressions. So now, at the top, no matter what epsilon is, we still have some rank 2 expression for some tensor. And what do we get at the bottom? Well, in these terms, the powers of epsilon cancel out with each other, and they're exactly equal to our tensor A we care about. And all the rest of the terms have some positive power of epsilon in front of them. So as epsilon gets smaller and smaller, we get a sequence of rank 2 tensors that converge to our tensor A, and it shows that it has border rank 2. So this kind of technique we just use for transforming from a tensor B to a tensor A is called a monomial degeneration. So like transferring from B to A by multiplying by powers of epsilon like this. And it's denoted with this B triangle A thing. And by the same kind of argument we just gave, if there's a degeneration from B to A, then the border rank of A is less than or equal to the rank of B. And more generally, you can even see border rank of A is less than or equal to the border rank of B. So as a reminder, our goal in these matrix mult algorithms is to give border rank upper bounds for matrix mult tensors. And so one approach to kind of trying to do this is to find tensors B that we know have low border rank and show that they can degenerate to matrix mult tensors. And this is basically what all the best known matrix mult algorithms do. So to be a little bit more precise, here's how all the best known algorithms work. They choose, in a very clever way, they choose a tensor T so that first of all, they show that the border rank of T is small, usually by explicitly giving some border rank expression for it. And second of all, they show that T, or a tensor power of T, if you don't know what tensor power means, it doesn't matter too much. It's kind of like a polynomial power of the tensor. The tensor power of T can be degenerated into a matrix mult tensor for hopefully a relatively large M. And then when you combine these 2 together, you get an upper bound on the border rank of the matrix mult tensor, so you get a lower bound, on what omega is. An upper bound on what omega is. Right. So what kinds of tensors T's have been used? Well, Strawson's algorithm I showed you before, it can be thought of as using T to be the 2x2 matrix mult tensor itself. But then, well, a lot of the work uses tensors which are not matrix mult tensors. So one of the first ones was Strawson's 86 algorithm, which used this so-called Strawson tensor. It doesn't really matter what it is, but you can check it's not a matrix mult tensor. And then lots of work has been done since then with more and more complicated tensors, and the most recent work since Coppersmith-Winograd all the way up to the best known bounds on omega used this Coppersmith-Winograd tensor, which once again, it doesn't really matter exactly what this is, but it's some tensor which is not a matrix mult tensor. But what I think is interesting about these tensors is that they're really nice expressions to show they have low border rank and so on, but I feel like these expressions all seemingly come out of nowhere. Just like Strawson's algorithm starts by saying, notice this crazy rank 7 identity. Similarly, all these start with crazy identities like that. So finally, I can tell you what our results are, and here, for the rest of the talk, I'm gonna have this general strategy in this blue box at the top. Okay, so our first result is a unifying framework. So what we show is that there's a particular tensor, or family of tensors, like T1, T2, T3, and so on, which I'll define it on the next slide, but they're the structural tensors of addition mod Q, such that, first of all, TQ has a really natural rank expression. It's really clear to see why it has the rank that it has. And second of all, for all the tensors T used since Strawson's 86 algorithm in this blue box way to give bounds on omega, our TQ tensor can degenerate to T via a really simple monomial degeneration. So another way so for all these tensors I was telling you about before, we can find nice simple degenerations from our simple tensor TQ to all those other tensors. So another way to think about this is that all the algorithms, all the bounds on omega since Strawson's 86 algorithm, instead of using these more complicated tensors in the blue box, they can all be achieved by using our TQ tensor instead. So let me show you what TQ actually is. So here it is. It's this nice, really symmetric looking sum. The indices are from 0 to Q minus 1, and it's just all the terms where the 3 different indices sum to 0 mod Q. So that's why it's related to addition mod Q. And it has rank Q, and the rank expression follows basically from a discrete Fourier transform kind of thing. So if you let W1 through WQ be the Qth roots of unity, then here T sub Q is equal to the sum over for each of the Qth roots of unity, W to the I times Xi times W to the J times Yj times W to the K times Zk. And you can check when you expand this out, these terms here, when I plus J plus K is not 0 mod Q, then all the different roots of unities are going to cancel each other out and the term will go away. So this is, I think, a really nice natural expression showing that the tensor actually has rank Q. And then I'm not going to show them to you now because it's more annoying than interesting, but there's really easy monomial degenerations from TQ to all those other tensors I was talking about. I think if any of you in the audience was given the definitions of all of them, you could very easily. Yeah, they're all very small. The best known one used Q equals 7, and Strawson's used Q equals 8, and ones before that. I think the bounds that were best bounds at the time used 6, 7, or 8 for Q. Yeah. Okay. Yeah, so with this in mind, let me tell you our second result, which is sort of, I guess, the namesake result of our paper, which is a limitation of using TQ in this blue box way. So what we show is that for every fixed Q, there's an explicit constant VQ, which is bigger than 2, strictly bigger than 2, and such that using TQ or any degeneration of TQ as the tensor in this way to get bounds on omega can't give a matrix mult running time of better than n to the power of VQ. So if you use TQ or a degeneration of it to get your bound on omega, you can't get omega equals 2 in that way. So for example, the best known bound on omega by Legal uses T7 to achieve 2.3729 about, but by comparison, we show that no degeneration of T7 can possibly get better than n to the power of 2.14. And here's a graph I made of what these kinds of bounds look like. And again, all the known algorithms use 6 or 7 or 8 for their TQ. So by, I guess, contrast with this kind of bleak note, there's, yeah.
Is this the order of quantifiers here? So, I mean, it's for every Q there is an explicit constant, VQ larger than 2, or do you know that there's an explicit constant regardless of what Q is.
Yeah, for every Q, there's an explicit constant. And actually, so our last result or observation is actually that as Q gets bigger and bigger, this constant VQ actually goes to 2. So I think even though at first there's kind of a sad limitation, I think this is actually an exciting approach to trying to prove better matrix multi algorithms. Because instead of focusing on specific cases like T7, maybe we can try to come up with expressions that work better and better as Q gets larger and larger and try to achieve omega equals 2 in this way. But again, all the known approaches we know, after you get above 8 and 9, they sort of get worse and worse as you increase Q. So let me very quickly sketch how the lower bound works. And I think this is going to be I'm going to say things that are technically false here, but they're almost true. If you know about these kinds of things, I'm going to say degeneration when I really mean things that are slightly different from degeneration. But anyway, here's the idea of how it works, and it's actually a fairly simple proof, I think. So just one quick definition. We'll say that a tensor A is independent if no two of the terms in it share any variables at all. So here's an example of an independent tensor. So we're going to use this result from this recent really breakthrough from extremal combinatorics that started by Ellenberg and Gijswit on the CAP-set conjecture. And one result you can derive from all the things that they've proved, if you massage the things a little bit, is you can show that there's no degeneration of our TQ tensor to a large power into a large independent tensor as n grows large. So you might think that you can degenerate TQ to a large power into a tensor of asymptotically the same size, but you can use the result to show, no, for any fixed Q, there's no degeneration of TQ into a large independent tensor. So how are we going to use this? So just a reminder, what we're going to show is that for any fixed Q, using TQ can't yield omega equals 2. And the idea is this. Well, what we first show is that actually in matrix multitensors, you can degenerate them into big independent tensors. So there is one of asymptotically the same size as the tensor itself that you can degenerate it into. And so if you had any tensor T, and you used it in this blue box way to prove omega equals 2, that means you can degenerate the tensor T into a big matrix multitensor. And if T were our TQ tensor, that would contradict the CAP-set theorem. So it's I think, a really simple but a really cool idea. But it also shows that sort of our bound, but also the fact that it goes to 2, the lower bound goes to 2 as Q goes to infinity, is kind of very inherent, because actually as Q goes to infinity, there are independent tensors of closer and closer size to what you would need to find a big matrix multitensor in the TQ tensor. Okay, so I'll quickly mention, I think I'm about out of time, but there are kind of 2 other past works on limitations of matrix multi algorithms. So the first one by Bainis et al., they showed a lower bound for algorithms that use the so-called laser method. So the laser method is a way, basically, for the second step in the blue box of showing how your tensor degenerates to a big matrix multitensor. It's a particular way to do that when your tensor is the Coppersmith-Winograd tensor. So and almost all the most recent algorithms use this laser method to do that second step. So they show that if you use the Coppersmith-Winograd tensor and you use this laser method to degenerate it, then there's a lower bound. And their lower bound is actually a better lower bound than what we prove, but it's for a more specific class of algorithms. So they have to be using Coppersmith-Winograd tensor, and they have to be doing the degeneration in this type of way. Okay, and then the second recent limitation is this paper by Blasiak et al., where they showed lower bounds for the group theoretic approach to matrix multiplication that I don't think I have time to say very much about it, but basically it's a different way to look at matrix multi algorithms from the perspective of group representations instead of tensor rank. And they show that various groups in that approach can't achieve omega equals 2. And they actually also use CAP-set conjecture stuff in a somewhat similar way. Yeah, so I think it's a pretty cool paper. Yeah, so just to conclude, here's a summary of our results. We show that all the matrix multiplication algorithms since Strassens can be achieved by using TQ for a fixed Q. And second, we show that TQ for a fixed Q can't yield omega equals 2, but we think it's a promising approach that as Q gets larger, maybe TQ could be used to prove omega equals 2. Yeah, thanks. Yeah.
So did I understand this thing correctly, that you say you want that all big start with this extensor, or is it
Uh,
still have to go through the order proof?
So the proof of the border rank expression becomes simpler because you just combine our DFT with like a really simple degeneration. The second step where you degenerate to a matrix multensor is exactly the same. Yeah. Yeah.
There are all these numerical coincidences in the group theoretic work of Koenig et al. That they achieve exactly the same exponent as Strauss's 2.48 algorithm and exactly the same exponent as Strauss's 2.41. Is your observation that CWQ is the generation of TQ in hindsight explain those coincidences, or is it just another interesting echo of the same?
Yeah, that's a great question. So Virginia and I, we've been working with Henry Cohn a bit, and we're like trying to figure this out. So the short answer is, I think there must be a connection here because the things are really similar looking to each other, but I don't actually know what the connection is, but we're working on it, and hopefully soon we'll have a better answer. Yeah.